Okay, bom dia, good morning. So we are studying, let me put it like this, a recent research project in math modeling plus numerical modeling, which is the main part of this course, plus scientific computing. And I'm trying to tell you this story, right, that starts from math modeling. The math modeling very sort of superficial. Some more of this, usually some of this, not exactly this problem, in the PDEs and applications course, a little bit in the fluids course, but this is the numerical course. So, right, so I want to show you. So let me recall from last class the motivation for this problem. So the motivation came from the acoustic waves to water waves in a heterogeneous medium. So the acoustic waves, is that layered medium like this, and you send the wave through this medium, and you have the transmission and reflection, and there's many interesting phenomena, in particular when this medium is random. So random, or a better word, disordered, with no structure. Because if you do say random, which Papa Nicolau and collaborators had some theory using doing PDEs with random coefficients, so it uses probabilistic results, right? But actually, the thesis of my first student, Juan Carlos, which is what I'm going to tell you, we thought first of it as a disordered medium. So we didn't really use, in the theory, any probability results. That we did afterwards. I did afterwards. Okay, so this is the story. So there was some theory for this problem, and we wanted somehow then to do the mathematics and the numerics for this problem of a long wave like a tsunami interacting with this piecewise constant topography. Even though we don't see this in the ocean, but as a mathematical exercise, it has an analogy with this, because here you have piecewise constant speed, and here you have piecewise constant speed disordered, meaning it's not periodic, right? There's no order in a rapidly varying scale. But this problem originally is 2D. I showed you the equations last time. Potential theory, complicated, and so on. We have Laplace in here, Neumann here, free surface conditions, and so on, so on, so. So the first part was math modeling, which actually I can call it also reduced modeling, which is getting a mathematical model that's more complicated and mathematically reducing it in an asymptotic way, having control on the regime of interest. Long waves, blah, 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 okay? So I indicated this last time to you that we did this. So the math modeling used conformal mapping, which you can do it in theory, and actually you can do it in the computer. And I promised I'll show this to you, not today, in the near future, this free software, which is beautiful, by Driscoll, okay, Toby Driscoll, and so on. So, okay, we can do the conformal mapping. Well, what did the conformal mapping did? We were able to map this onto a flat bottom case. This is then, let me say, okay, here, x, y, here, xi zeta. This is the complex. I can think of this in the complex z-plane, and here I can think of the complex w-plane, okay? And, and then from here, I was able to simplify my problem. Let me write the equations and get a, what I called in that paper that I gave you last time, right? The reference, terrain following Boussinesq system. And let me write it down for us here, for us to remember. Okay, where m is equal to, or let me put it this, m squared is equal to the Jacobian of the change of variables evaluated at zeta equal to 0 which is the free surface, okay? So here I ask you to believe what I'm saying, because all I said up to here is more from the, I could show you all the details of this in the PDEs and applications course, right? At least how to deduce this equation without these variable coefficients in the flat bottom case. We see this in both in the fluids and the PDEs course, okay? Now you have never seen it with conformal mapping, change of variables, blah, blah, blah. So this is one of the things I ask you to believe on me. This comes from the square root of the Jacobian evaluated here at the free surface, which is good news because you're away from these corners which are singularities of the conformal mapping. I will show you today graphs, pictures of this coefficient, which you see how intuitive it is. It's kind of cool. I like it. When I saw it, when I was able to do it for the first time, I said, oh, this is good news. I want to show you these good news, okay? The other thing I want to say is, okay, we have, remember that alpha is the nonlinearity parameter. Beta is the dispersion parameter. You know what dispersion is, right? Let me maybe remind to you, and also that we have here. This is the nonlinearity parameter. This is the dispersion parameter, where this is the depth, this is the typical wavelength, and so on. Okay, and this is the typical amplitude. And these are, I'm going to think of this as order epsilon, and therefore weakly nonlinear, weakly dispersive mathematical model. Okay? Now, still going back, salesman talk. I'm a salesman trying to sell to you this project, this model, and what are we going to do? Okay, so first step, this actually continued. I will not tell you in this course the whole story, but this started with then Juan Carlos Munoz, and I said, look, there's all this theory for this problem here, which is a hyperbolic, linear hyperbolic system. So let me write this also here. And this is a nonlinear, weakly nonlinear dispersive problem. Oh, but is there a connection? Yes, there is. And that's where then my mathematical curiosity started. And I asked the student, let's start double checking if my ideas are correct. So first thing is, look, in some of the papers here, some numerics have now been done basically with a hyperbolic system. So from the mathematical point of view, I say, let's start, and this is how we do, right? We start with a simpler part first, and we start making it more complicated as we succeed, as we have success with the ideas. And it happened that way. I wasn't sure it was going to happen that way, but I had a strong feeling it would happen that way, And it worked, right? With good students and so on. So, okay, let's think of this as a perturbation of what was known for linear acoustic waves. Well, this is simple. If this is linear acoustic, right, let's start. So we started, and put here, started with alpha equal to 0, beta equal to epsilon. Why? Because if I put alpha equal to 0, I kill this guy, right? This term is not here anymore. I just get du dx. This term is not here. So this is a epsilon perturbation of a hyperbolic system. Okay? So we did the theory, and we did the numerics. And we actually did the numerics. I'll show you some of this today, also for the hyperbolic problem. Because the paper we used, there was mostly theory and no numerics. So we did the numerics for the hyperbolic problem, which is an analogy with the acoustic case. Okay? So figure number 1, you have it up there. So that's a figure I did by hand last time. So what I did is, remember that I said that I used the paper by Hamilton. Well, let me not write, just keep it this here. So I'll use my hands here. So think of this, look. Let me erase this now, erase the wave. Okay, and for technical reasons, for the expansions to be done, it is useful to create a symmetric mapping domain that you're going to map. So remember that I reflected this here above, right? I know that my domain of interest is the lower part, but mathematically I can reflect it above, and I'm going to map this reflected domain to a strip, which actually is a strip that also has a part below and above. There it is, and I'm going to show you how to use, okay, you can maybe go up here. I'm going to show you how to use, at one point, the Schwarz-Christoffel mapping. So look, I have a polygonal domain with 2 mountains on the bottom. I reflect the mountains on the top, and these lines you are seeing are basically the curvilinear coordinate system, orthogonal curvilinear coordinate system I mentioned last time, which in the canonical domain, it's a Cartesian coordinate system. It's the C zeta coordinate system. And since conformal mapping preserves angle, look, my hands here, right? Angles, it will then if it's a curvilinear, it will preserve these angles. So we see, and actually we see the undisturbed free surface is the line of symmetry, which is a undisturbed free surface in the physical domain and in the computational canonical domain. Okay? So this is very nice for us to see the conformal mapping, so the symmetric flow domain. And these equations here, right, are the equations now I'm going to, at one point, solve. Okay? And the theory that Juan Carlos did, I'm only going to tell him, sometimes we actually read a little bit of this in the PDEs course. I'm not going to do it here, of course, because it's a numerical course. But actually, the theory that was done, which I'll just tell you the result, was for alpha equal to 0. And the numerics we did was with alpha very small, but we left it there just to see if it was not important in the dynamics, okay? Okay, so what else I want to say now? Yes, let me show you, I think in the next figure, let me show you also the Jacobian. So the next figure, I'm going to show you this, if I have it right. If not, I'll skip and come back. So if we know some results too for periodic bottom, okay? So here's a periodic bottom, periodic set of triangular mountains in the bottom of the ocean. Of course, this is a mathematical idealization, but it's very important as a numerical test for a problem. So those of you who did with me PDEs and applications or fluids, you might remember that I mentioned the paper by Rosales and Papanikolaou, where we had a very rapidly varying periodic bottom, and the periodic bottom generated no reflection, but just sort of changed the speed of the wave. Okay, it was in the homogenization kind of regime. So there are many regimes where you can study the periodic waves. I'm not going to, periodic bottoms, I'm not going to mention. But look at this now. Now I'm going to show to you, okay, as I vary this scale here, I'm going to show to you how m of xi, which is the square root of the Jacobian evaluated at 0, so here, say C zeta, sometimes C zeta is on the bottom, it doesn't matter, right? Conformal mapping, where you put the origin, it doesn't really matter, right, the translation. So I'm going to show you figures now of how this coefficient looks like for the conformal mapping of this guy, okay? And let me actually show the figures and then discuss with you. Let's see if I can page this from a distance. Yes, yes, yes. It takes a while. So here, okay, here there's one figure before that I had forgotten. Look how nice you see. This is just the lower part. This is just the lower part of the domain with a few more mountains now. And you see now very nicely why I call this the terrain following Boost-Nask system. You see the lines are kind of following the terrain, right? So the lines follow the terrain. We see it up here. And that's why it's the terrain following Boost-Nask system. And look how the curves meet the boundary at the 90-degree angle, like here, here, right? The vertical curves, right? So it's preserving angle. Okay, now let me show you the Jacobian as we plot it at the free surface. It's going to appear just in a second. Excuse me. Here it is. I have to, let me just go over here to lift the picture. Oops. Oh, I'm sorry. I sat on the microphone, sorry. Oh no, here's another important figure. Let me show you, let me discuss this with you before. This is a very nice figure. I like this figure very much. It was very important in the paper. This figure showed to me that, I'm in business. So what does this figure say? Then I'll show you the Jacobian, okay? Sorry. This figure says this, look, if on the left, we see just what I showed you before, a topography with, say, 3 mountains and my terrain following curves, okay? If you think, at some talks I received sometimes criticism from people saying, oh, but if you have these boundaries, how about, near the bottom, there's like drag, could be vorticity, there could be other things. Well, the nice thing here is that this model, and actually was shown in the laboratory by one person long ago, that this model, long wave model, is good as long as vorticity generated on the bottom does not reach the free surface, okay? So this model is good if you're observing waves on the free surface, but it's not a good model, mathematical model, physically speaking, very good if you want to check in detail the flow near the bottom. And this is one way of getting some intuition also why the conformal mapping helps you when you do the power series expansion. Look, I chose over there 10 lines, just to draw 10 lines to foliate my domain. Over here, I think I chose 100 lines. So, of course, the conformal mapping is going to foliate the whole domain, right? Because it's the horizontal lines. But it takes a long time for it to reach the valleys of these steep mountains. And one thing I haven't told you is that the original Boost-Nask system is a depth-averaged method. I think I mentioned this last time, now I recall. They said, look, when it's a long waves, the velocity does not change very much in the horizontal direction, so one way Boost-Nask did was to average it over the depth. Those of you who did PDEs or fluids with me might remember that, okay? So if I now average it in the complex variable, in the curvilinear coordinate system, look what happens. That part that's white below on the left here, look at the left graph, the part that's white below the last level curve towards the valley counts 10% of the average. Why is that? Because I only have 10 level lines, so each sort of block of level lines is 10% of the average. If I average over a curvilinear vertical line, right, each sort of layer is counting 10% if I have 10 curves. Do you agree? So the one below, close to the bottom, counts 10%. Now, when I put 100 lines, that shows that below the last curve, down to the valley, that region in the average will count only 1%. So that shows somehow that if I do the averaging, let me say it again, if I do the vertical averaging over a vertical curve using the conformal coordinates, I'm in better business than using the Cartesian coordinates, because that lower region there below the lowest curve will only come into my average counting 1% in the region where we know that the model is not the best. Okay? So that's somehow an intuition why things work better in this coordinate system. Now let me show you I think now I'm going to show you the figure of the Jacobian. Let's see. Yeah, here it is. Maybe I should roll the screen a little bit. Yes. So here I'm showing two things in these figures. This curve here you see on the top is the Jacobian. It's this m coefficient here, okay, that you see here. It's this m coefficient plotted here, right, for mountains like this. But over there I have like 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, okay? So first what I did is this, 1, 2, 3, 4, 5, right? These mountains are the same. And if I, see it has corners, but if I conformally map this and look at the Jacobian on the free surface, it's that smooth curve over there, which basically tells us when we compare that, basically you don't see the sharp corners, and it's a smooth, m is a smooth coefficient, okay? The other interesting thing I'm showing there, looked at the graph up on top, has 5 peaks and then it comes down, and there's then 2 more peaks to the right, okay? Even though conformal mapping, as we know, complex variables is something that's non-local, right? You're solving a problem that's non-local in the sense it's a harmonic function. So it's like Laplace's equation. But this thing has an interesting thing. That's why the Schwarz-Christoffel toolbox was so nice. If I add 2 more mountains, as you see there on the right, you see that basically the coefficient just spreads out a little more. So it doesn't really change the Jacobian over the first 5 mountains. So actually this is good news. Almost you have a local effect, even though the Jacobian is something that's non-local, but it has a local effect in the mountains. And the effect of the mountains decays exponentially fast outside the region, namely here and here, okay? And then another good news, interesting news from the conformal mapping. Now, let me say that I'm going to get these mountains here, and I'm going to do this. Let me put it here on the side. No, yeah. So now I'm going to do this. I'm going to make the mountains vary on an even faster scale. Okay, see, these are more spread out, and now these are faster. What this lower picture says, which is very nice, is that these mountains that are more packed together, when I plot them on the free surface, if I compare the Jacobian on the free surface with this, I see this. So that means that when the mountains are rapidly varying, the free surface cannot quite feel the deep valleys, right? It feels, and actually, I don't think I have a figure. Let me see, actually I have it here to compare. No, I don't have the figure because I didn't put in the paper, there was no need. Is that if you make the bottom, very, very rapid varying, it almost looks like a smooth step. So basically, eventually, if I make this even faster, like this, over the free surface, it's going to be basically something like this. Okay, so the conformal mapping has actually brings very nice properties of the PDE to some extent, saying that if I have a rapidly varying boundary down there, actually the reduced model or the potential will see that Jacobian will tell you on the free surface that this is effectively something smooth and actually doesn't vary. Okay, so it's a little bit like like we saw homogenization effect and so on. Okay, so these are facts. I can see from your expressions, and it's normal, natural, that you're saying, should I believe what André is saying or not? Because, right, I'm not giving you the details, right? You cannot mathematically understand all the details because I'm telling you a story without details, right? And this, up to now, is more also on the PDE side. And this course is numerical PDEs. So now, I'm going to talk a little bit now on the numerics and what did we want to do with the numerics, okay? So we have this system. We see some aspects of the conformal mapping. I still owe to teach you how to use the conformal mapping numerically. And we have all these pictures. Then we go to another article. So the first article was by myself. Then I'm going to show you a little bit the first article with Juan Carlos Munoz of his thesis, that what did we want to do, okay? So we wanted to do, let me maybe erase this to get preserve some space. So we wanted to do now a wave. Let me erase this, let me use this space now. Okay. So there's one thing that was known from Papa Nicolao's work first, is that if we have a channel, if we have a region where we have a rapidly varying periodic bottom, like this, or the bottom could be like this, and if we have a half space like this, and here random, it is disordered. Periodic, both rapidly varying. Here's the wave. Okay, they're both rapidly varying. The dynamics of the wave here versus here is very distinct. So there's mathematical theory for this. Here, for you, this is like storytelling, right? I'm telling you things. I hope you kind of understand, but you will not necessarily need to understand, and I think will not understand mathematically why that is so, because I think it's non-intuitive. And my intuition was very much acquired by numerical computations and the mathematical theory. So look what happens. Think that, let's think this way. This is on an epsilon scale, this variation. This is also on an epsilon scale. And let's say that the wave is basically normalized to having width 1. Okay? So if you get a periodic bottom and then you make it disordered on the same scale, right? To me, first, this was not intuitive. The dynamics is quite different. And in what way? In this regime, most of you here have seen me present to you some of the results, for example, of Rosales and Papanicolaou, okay, which is a paper that's cited in those ones that I have. So Rosales. So this is Studies in Applied Math 83. which is a MIT paper. What did they show? They show that this wave, if it's a solitary wave, it propagates in this direction, and it has a slower speed. Even if this excuse me, even if this bottom here is mean zero, okay, goes up and down, excuse me, it propagates with a speed slower than 1 if we normalize the speed to 1. It sort of has an effective speed smaller than 1 due to the microstructure. That's the jargon of this theme of waves in heterogeneous medium. Again, what is a wave in heterogeneous medium? Is a wave in a medium that changes. A wave that in a medium that changes, how? It can change in many ways. It changes because its propagation speed changes, has a structure. In this case, a periodic structure, rapidly varying, and it's amazing that you have no reflection and the wave just moves slower. It feels like it's in some other medium, a homogeneous medium. If the medium is perturbed a little bit, doesn't have to be much. I did this numerical, and it's random, or better said, disordered, which means no structure, right? Disordered means no order, right? And then if one wishes, mathematically, and that's what Papanicolaou collaborators started doing for the acoustic case, they said, okay, if I have a disordered medium, a medium with no order, in what? Okay, in the propagation speed, it has no order, then I can mathematically say, okay, it's a random medium, right? On the planet, there's nothing that's really truly random medium. Random is a choice that we do to model, to understand, say, uncertainty, for example, right? And for waves in the crust of the Earth, you don't know what's down there. They wanted to study oil. So uncertainty is a good way to add information to a problem. And then what is the information you're gonna extract? Is you say, okay, for this class of uncertainty, I can say this and this and this about the wave. Okay, for example, the expected value of the transmission coefficient, of how much energy is transmitted. Okay, that's a mathematical way of thinking, right? Because nothing is random, but you add uncertainty to your model. And one way you can add uncertainty to your model, for example, for this acoustic problem, is that you say, okay, my medium is, for example, one idea is uniformly distributed. The propagation speed, for example, is uniformly distributed from 1 minus delta to 1 plus delta, right? I'm talking about a normalized problem. Mathematically, we normalize. So if you normalize, you say the speed is 1. And then Márcio tells me, oh, no, I heard that the speed here is 0.97. And then Lucas said, no, I heard it's 1.02, whatever. Then we decide, okay, it's going to be normally distributed, 1 plus or minus delta 0.3, or whatever. You can also make it normally distributed. But the simplest case is uniformly distributed. It could be anything with equal probability within 1 minus plus or minus delta. Okay? And then that's the constant case. Okay. So then what they showed in, which is non-intuitive at first, that if you have a disordered medium, that you model it, say, as a random medium, but if you have a disordered medium, let's just think disordered medium, that's what we did in this paper. We didn't put any probability. When we put probability, I needed help from some friends, as I mentioned, Jean-Pierre Fouque, Jocelyn Garnier. So in this, when we put disorder, instead of the wave propagating with no reflection and just changing its speed, it still changes its speed, but it generates reflection. When it's randomness, it generates reflection. This is not intuitive, and I will not make an attempt too much to explain here. I will just give you one information later on. And it was shown, it can be shown that mathematically that this reflection process, this way that energy comes back from the wave, is diffusive, like I mentioned that to you, apparent diffusion. It looks like there's a diffusion mechanism in the equation, even though there is no diffusion coefficient in the equation. So this looks a little bit very mysterious. When I saw this first time, super mysterious, looks a little bit like, almost like science fiction. Should I believe this or not? And that's what I'm going to show to you now, a little bit how we did the numerics. We have time in this class. And I'm going to start, if time permits, I'm going to show you how we did the numerical method, because this is a numerical method course. Okay? Or maybe let me do the other way around. I think I'm going to do the following. I'm going to show you the figures first, and then show you the numerical method. I think I'll have time for both today. But I think it's important for me to show the figures so you start getting the intuition that I acquired by studying the problem. When I first heard about this, I had an expression in my face just like yours, like, how does this happen? Okay? So let me show you some figures of the other paper and tell you what we're going to do. Yes, Lucas?
The diffusion is due to the numerics or to the mathematics?
Very good question, and I'm going to talk about it. The diffusion is not due, so the question is for the diffusion is not due to the numerics. The diffusion is due to the variable coefficient. And we have to do numerics. This is exactly the first point I'm going to get at. We have to do numerics to show that we have no effectively speaking, numerical diffusion, so that we know that the diffusion comes from the numerics. And that's exactly what I was going to maybe draw on the board now. So what I'm going to show you, before I show the numerical method, let me show you exactly along the lines of what you asked, what was our numerical plan for the scientific computing of the respective numerical modeling. Okay? I am not yet telling you yet, one thing very important in this course, what was our numerical choice for the scheme. So here's what we did. Here was the strategy in scientific computing. So we will put a pulse at time zeros like this. Okay? So it's a 1D. It's a 1D numerics. So this is our eta of x0. Let me call it this. Okay? And so let me put like, okay, let me organize this. So this is basically the recipe, right? The working plan with Juan Carlos when we started this problem. He had done the theory first, but also was already programming. But the programming plan was like this. Number one, Juan Carlos, let's do a simulation for a flat bottom with a pulse-shaped wave. We wanted the pulse. So as a pulse, what did we use? Now in the class, Gaussian. And then we said, it's working so well for the Gaussian, let's try a solitary wave. Because this system here, you can cook up, you can write an approximate solitary wave, okay, for it. And we test it, and it travels on. But the solitary wave is weakly nonlinear, weakly dispersive, sorry. Weakly nonlinear, weakly dispersive. And then after we saw that the theory from Juan Carlos was working so well, we said, it's a linear theory. But said, well, who cares? Everything's so good. Let's test the linear theory for a weakly nonlinear case. And to our satisfaction, it worked. Okay, so I'm going to show that to you. Maybe not today, but maybe today, maybe next class. So okay, let's not lose track of our roadmap of what should we do. How should we do this research problem step by step? So number one, flat bottom, and you're right, start with a Gaussian, and also at one point do the solitary wave for the flat bottom. So I'm going to show you a picture in a second, okay, where we let this guy evolve for a very long time, as long as we need it, as we will need it to evolve for this case, okay? And we get it here at time equal t. We compare this guy with this guy, and they fall right on top of each other, right? Which means, so let me put it like this. And then I compare this here. They're right on top of each other, which is good news. We don't see any diffusion, and we don't see any dispersion. You know what I'm putting this circle here? Exactly, because the little oscillatory tail could be a little bit, could be big. Big is bad news. There could be a little bit, if I see a little bit, there's a little bit of numerical dispersion, right? So what should I do? I should then maybe change delta x, delta t, right, and get things better. If I'm doing the hyperbolic case, it's basically doing the current number equal to 1, right? I'm just actually now grading, hopefully finishing through your first set of problems, right? Okay, but I'm first going to do this, okay, for alpha equal to 0. The Gaussian case, I'm going to do this for alpha equal to 0 and for beta, what value? Not epsilon. Help me. So for this case, if I want to see this wave traveling like this with no tail here, 0, right, you got it, 0. Why? Because if I want to see that there's no numerical dispersion, I want to make my PDE non-dispersive so that I know that that little tail, like you did with your finger, is numerical, right? You see what I'm saying, Master? So that's why I'm putting beta equals 0 first. So alpha equal to 0, beta equals 0. I'm basically doing the exercise that you did in your set of problems, right? But not with Lax-Wendorf, not with upwind, with another method that I'm still got to tell you what it is, okay? But you see why, right? So I want to make sure no numerical diffusion, no numerical dispersion. So therefore, I switch off nonlinearity, I switch off dispersion, and I get my Gaussian to be a traveling wave, nice and clean, okay? So that's what we do. And then we check a little bit, then to make sure that the dispersion is also good, then we let alpha small, beta small, we put a solitary wave, and because the solitary wave needs dispersion and nonlinearity to balance each other, and we get a traveling wave, solitary wave. We say, okay, we're taking care of nonlinearity and dispersion in a nice way. If our solitary wave had a little tail starting to appear, I would then calibrate delta x and delta t, right? We don't quite have a current number anymore. It's a dispersive equation, but calibrate it to clean it. And that's how we found a good resolution in space and time by putting our solution in the flat bottom case. Okay, that's simulation number 1. Then, so basically, simulation, I would say number 2. So this is what I should say, alpha equal to beta equal to 0. And here, alpha equal to beta equal to epsilon flat bottom solitary wave. Okay? Then simulation number 3, which does not appear in the paper, and I think simulation number 1 with the Gaussian is also not in the paper. We did it for ourselves. In the paper is the solitary one. We'll see. Okay, I think we didn't do it, the 0. And simulation number 3, not in the paper, is rapidly varying periodic bottom. This case. Why? Because then we knew, like with Juan Carlos, we knew, okay, we're good with a flat bottom case, hyperbolic case, no dispersion, no diffusion. We're good with the weakly nonlinear case, which helps us know if there's numerical dispersion or not. We get a traveling solitary wave, gone. Okay, now the trouble starts, the real trouble starts, because now we want to check, to have a good numerical method for a wave traveling over a microstructure. So I need now to understand how am I going to resolve in the numerical jargon. You know what resolve in the numerical jargon means? Resolution, right? How many points do I need to put in my microstructure so that I get a good result? Okay? So then what I did is that then instead of mapping this, so we did something, and actually one referee asked us and said, look, we're actually playing against ourselves. So since this is going to be a very complicated conformal mapping because it has many points, it will take forever, and it does. Actually, the Schwarz-Christoffel toolbox, if you have too many vertices, the memory cannot deal with it. So can you imagine here, like, I don't know, 1,000 vertices. So the Schwarz-Christoffel method could not deal with it. It said, okay, so we're going to play against ourselves. We're going to actually put this rapidly varying guy as it is without smoothing and so on as this coefficient here directly without mapping. Okay? So that's we're making our lives harder because this coefficient should be smooth, and we're going to put something not so smooth, but it's okay. Numerically also you discretize things. So anyway, so we put this here, and we let the wave go, and we more or less see that, okay, our delta x, our delta t, we get a solitary wave, for example, or even a Gaussian, I forget which one we did, maybe this, traveling with a different speed and without generating any reflection and no crazy thing, no numerical instability, nothing. So that is evidence that we have our numerical method now fine-tuned experimentally. What do I mean experimentally? There's no theory for that specifically, for how to tune in such a complicated scenario like this. Experimentally means using our PDEs intuition and trial and error, right? That's what I mean by experimentally. Oh, I think this is great. And actually, I tell you, with the experience we had, from everything, very quickly we basically got a good numerical resolution for the numerical method. I still owe you to show that worked well here, okay? So then we got this. All right, then simulation number 4. Which is disordered case and to illustrate theory of apparent diffusion. Okay? So the theory done by Juan Carlos in his thesis was basically based on the theory that some people did, Berlin and Burge. I mentioned this name. For the acoustic waves, and it's a form of asymptotics. There's a lemma in the middle, but there's no theorem for the whole thing, right? So we actually illustrated their theory, which is for the hyperbolic case, and then we illustrated also our theory in this second paper that I'm going to start talking now in the last half an hour of the class. Okay, so in the disordered case, what was shown for the acoustic problem, and that Juan Carlos also showed, it became more complicated, but we basically were able to do, we showed the following. So think of this now. Suppose that here's our bottom, our random bottom, piecewise constant or this one is better than the piecewise linear. Right? This is the piecewise linear, this is piecewise constant. So for this case, if you think of this as the right-going wave, and this is a left-going wave, or in other words, transmitted and reflected, so you can rewrite this system here as a right-going and a left-going wave. Okay, some of you know what I'm talking about, but if you don't, no problem. Just that a wave equation with two ways of propagation, two directions of propagation, you can write it in one direction, the other. Then what the theory says, is that asymptotically, for L large, what is L? L is this distance here, which means large propagation distances. That means if you let the wave propagate for a long time, interacting with this bumpy road, right? This reflection, this bumpy road. If you let this propagate for a long time, asymptotically, you can show that R, that is the wave R that has survived this whole medium, R is asymptotically a Gaussian convolved with eta 0. Okay, the Gaussian depends on time. Okay, so what is this? This is the solution of the heat equation, right, to some extent. And there's one trick also, that this has to be on a special moving frame. Let me not get into that detail. But anyway, this is the right-going wave, that is a transmitted wave, is asymptotically a Gaussian convolved with initial wave profile. Okay? So Berliand and Burridge, which were the first ones to do this for the acoustic waves, called this Gaussian I have to breathe first or else I'll say, it's a long word, I get confused. Stratigraphic filter. Filtro estratigráfico. What does that mean, stratigraphic filter? It means for the acoustic waves, here, they did this case. This is a stratified medium, right? And every time the wave feels a different medium, there's an energy that survives and something comes back, like an echo. So this multiple scattering, this bouncing back and forth, filters energy out of the wavefront. Okay? And in the proper regime, what is shown in Amazing is that in the proper regime, the filter is Gaussian. So this is the language of signals. So if you're interested in signals, okay, so let me give you an example here. Look at this. If I have a function f, and f hat, I go to Fourier, okay, and f hat, let's put it this side here, is a function like this. Okay, it's band limited. Its band limit is like this. If I multiply it in Fourier by this, look, this is 1. So let me call this H. So if I do H convolved with F, let me just call maybe F better. So the yellow curve is F. Look, this is a word exercise of signals. Okay? So this is the real part of my spectrum. This is K for this function f of x. Okay? So this is the first test. If it was a Gaussian, it would be a Gaussian. Now, if I do the convolution of this f, sorry, this is f hat. Sorry, this is f hat. Okay? This is a filter. That's why I called it f. Right? Because this convolved with this in Fourier is this times this. Okay? And if it's this times this, and this is 1, it means I'm only going to keep this part of the spectrum of f. Let me highlight it. Do you agree? So it's going to filter, it's going to throw out all this part. Okay? Now, if f is a Gaussian, let me try to imitate the same curve, and this is, say, 1. If f is a Gaussian, and I multiply f by f hat, this means it's also a filter. So do you know the name of this filter? In English, the most simple filters there are, I just remember this now, is a high-pass filter and a low-pass filter, right? Which one is this? That's correct. Melvin said it right. It's a low pass because it only allows the lower frequencies to pass, to survive. Okay? Very, very intuitive, the name. And it removes the high frequencies. Okay? So the Gaussian is also kind of a low-pass filter, but it does not remove all the frequencies. It basically just attenuates the high frequencies. Do you agree with that? Is that clear? Right? So this Gaussian filter compared to this one, which is the indicator function for the interval, this one just sort of attenuates the high frequencies. Look, but if you have a Gaussian filter, you have also something which is like the kernel of the heat equation. You agree? So therefore, this is why, if you can show mathematically, and they showed, and also Juan Carlos showed, that to leading order you have a filter which is Gaussian, or you have a convolution which is Gaussian with your initial condition, then you can call this, as Berliand and Burge called, a Gaussian filter, or a stratigraphic Gaussian filter. Why stratigraphic? Because stratified. Or we decided to call it a apparent diffusion, because there's no diffusion coefficient in the equation, so therefore it's apparent, or it's like an effective thing of the dynamics, but it's a diffusion because the filter is Gaussian, just like the heat equation. Okay? And why is it this way? Let's see if you have already some intuition, right? Some of you have already taken other courses with me, but even if not, why is the filter like this Gaussian? Why the higher frequencies we hit harder on the higher frequencies when we do, say, this dynamics here. Let's see if we can, let me test your intuition. If you don't have, no problem. But it's something that I've acquired, of course, studying, working on the problem. And numerics helps me, and the approximate asymptotic theory helps me to, over the years, I'm old, as I mentioned, I'm older enough to maybe even be the grandfather of some of you, is that this intuition comes together, and at one point it's part of you, right? The intuition acquired from mathematics and from numerics and from physics. But actually in some of these problems, the physical intuition was the last one to come, because actually first came the mathematical one to help. Okay? So why do we have a Gaussian filter? Why high frequencies participate less? This is another way of asking the same question, but it's a good exercise. Why do high frequencies participate less in the right-going, the transmitted coefficient, after it has traveled for a long distance? Say it wrong. It's good. It's a good exercise. Like playing soccer, right? You practice, you're going to try to shoot into the goal, and you shoot it in the stands far away, but your aim starts getting better and better. Why do you think this is so? Why do you think that the asymptotic theory at the end gives you this filter? And maybe not the contrary, not a high-pass filter. A high-pass filter would be if this guy was here and would erase the other ones. Do you have an intuition? Feel free to say it, even if you say it wrong. No problem. It's good. Good exercise. Have fun with saying it, even if it's wrong. Because now we're playing. It's a PDE course, right? So I went from more standard book stuff now to paper to exercise with you things of research in the field. So say it, Mas. Okay, so Márcio said that he thinks that it's because the high frequencies ones, the high frequency modes are going to be less perturbed by this structure. Okay? So by this structure. But note one thing, and I think Melvin already made a sign. Let's see. It's good. Everybody trying to proceed. So one thing, Master, is that look that what I'm saying here is that the high frequencies are not participating in the right going mode, which means, because this is like a conservation problem, which means that they are present in the left going modes. So they are in the dynamics, okay? And the other thing I want to call attention to is that in this model here, which is something that might fool you a little bit, because your answer, I'll correct your answer, okay? So one thing that might fool you is that this model here everything has been collapsed to 1D, to the free surface. Okay? So mathematically here, all the modes feel the bottom. Okay? If I was in the 2D problem, it would not feel. But they're mathematically present here. So it's a bit tricky. I'm gonna correct your answer in just a second. I don't know if Melvin wants to say something. No? Okay, it's okay. So the reason why is because of this. Look, let's think, that's the intuition I had, and I remember at one point actually telling this even to my advisor and said, okay, that's a good intuition. My intuition for this is, and I think that will happen, I think of the wave scale as the scale of a tire. Okay? A tire of a truck, of a car. Okay? And I feel, my intuition is that the scale, and it works, okay? The scale of the bottom is the scale of imperfections in the road. Okay? So look at this. All of us here in Brazil, Latin America, we all have, you go a little out of the city, there's like dirt roads, right? Estrada de terra, dirt roads. And they're bumpy, right? Or even on our roads, there's those things that makes us, which we call quebra-molas, that makes us drive slower. So if the tire, if a bump in the road is at the same size of the tire, we feel it very strongly, right? But then if the bumps are on a very small scale, right, and the tire is wide, we don't feel it. Like, for example, in roads in Brazil, sometimes we have what's called sonorizadores, which are these sort of just stripes on the road that makes you just feel like you're getting out of the road, or you have to slow down because you have to pay the toll, the pedágio. Okay, so the thing is, now think of this. Let's think of the sonorizador. Okay, this thing that makes this noise like when you're getting out of the road. If I go with my car over a sonorizador, my car makes this noise, but it won't bump very much. Okay, but if I'm pushing a baby cart, which has a wheel that's small, on the sonorizador, the car will shake. It feels more the details. So let me go back to the answer now. So even though, so this is the tricky part. This is the tricky part, but very interesting, I think. Even though this model here is a long wave model, okay, because for beta small, right? Mathematically, if I do a FFT of the solution eta, in the Fourier spectrum, for example, if I have a Gaussian, if eta is a Gaussian, the Fourier spectrum goes all the way to infinity. Exponentially small because it's a Gaussian, but it goes all the way to infinity. So it has short frequencies, short waves in the spectrum, even though the physical wave is a long wave. Am I saying things correctly, right? So the shorter frequencies of the spectrum feel the details of the bottom more than the lower frequency of the spectrum. By this analogy of the baby car or my driving car over a sonorizador. Okay? So the high frequencies are reflected back stronger than the lower frequencies. Okay? And in this case, I would mean this is a lower frequency, and this is a higher frequency. If I do the FFT decomposition, of course, because a Gaussian, let's think of the Gaussian. A Gaussian in the physical domain is a Gaussian in the Fourier domain, which then means that the amplitude of this guy, or let me say it this way, the amplitude of this guy is exponentially smaller than the amplitude of this guy in Fourier space, because it's also a Gaussian. So the amplitude, right? But still, this guy is going to feel more the bottom than this guy. This guy is going to take longer, right? And in the right asymptotic regime, the way these guys decay is according to the Gaussian. Just like the heat equation. This guy cools down much faster than this guy if these were positive temperature in the heat equation. Okay? So that's why, that's why the filter is like this. The filter is saying that the high frequencies, now pay attention, this is a filter for transmitted wave, for the guys that are going that way. We're not talking about the guys that are coming this way. Okay? So the filter is stronger for those guys, and therefore it's a Gaussian filter. And therefore, if it's a Gaussian filter, it's like the heat equation, mathematically speaking. And even though there's no diffusion coefficient here, look, there's only a dispersion coefficient, not a diffusion coefficient. There's no UCC. Asymptotically, it's non-intuitive, asymptotically, the solution feels from this bumpy road, boom, 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 the solution feels like it's under a diffusive effect for the wavefront. And I'm going to show you now in the last minutes that we have, and then I'll come back to this next week. The very nice first simulations that Juan Carlos did that, are in this paper. Okay, let me just show you the figures, and then the numerical method will be for next week. But I think it's good that I show the numerical method with you already with the intuition of what we want to get out of it, right? So, okay, let me open then another paper. Okay, so see, this is a paper which was with Juan Carlos, SIAM 2004. So basically a year after the other one. Let me go. I'm not going to show you the theory or anything. I'm just going to go to the numerics, and then not the numerics. Next week I will tell you this is the theory. Then there's the numerics. The theory I might just say a few words just for cultural reason. Maybe not. I'll see. Maybe I'll say a few words. Let me go to the numerical simulations. So this is all theory. Here's the numerical method. Results. Okay. So here's the first results very quickly. And then I'll show, because I want to show you some with the random thing, and then I'll come back to this next week. Here is the flat bottom case. Okay, so let's look at the bottom one first. The bottom one is with a Gaussian pulse. See over there, initial Gaussian pulse. And it's exactly what I showed you. A Gaussian traveling over a flat bottom, hyperbolic case, and then at the end I have the numerical solution superimposed on the initial profile, and you cannot see any effective sign of numerical diffusion nor numerical dispersion. Very good. The other one is a more complicated one to test. It's a Gaussian, and we let it run. So now beta is equal to epsilon. It's small, okay? And we compare it with an Airy function. Okay, so we do this numerically using MATLAB, and we see that the dispersion is good. See, the oscillatory tail is for the Airy function, and things are good. So this is for the flat bottom. Okay, and now let's go for one so I can today, oops, I forgot this, show you one with a variable bottom. Okay, this is for the solitary wave, okay? Also the solitary wave in the flat bottom. And you see that the code is working very well. Okay, and here it is. Okay, so here was the first exciting result that Juan Carlos got. So on top is again just the initial condition, right? And then we let this initial condition, this initial profile, to travel over in a region with a disordered coefficient, where we had apparent diffusion. And the theory that the other papers do, and we do too, is called a near wavefront theory, which means that you put a window around the wavefront and you follow this wavefront. Okay, so it's a theory that should give you a good approximation for this guy, but here that's what we call the multiple scattering signal. What is this? This is because as the wave travels, it generates some reflection, right? And part of this reflection that goes back then bounces and comes back. So that's why it's called multiple scattering, which means it's little pieces of the wave, which we actually say in English you can say it reverberation. In Portuguese, reverberação, which means things that keep on bouncing back and forth, going right, left, right, because it hits. For example, something hits here, so it starts coming back, then it hits here, go this way, that way, so it reverberates, okay? So the theory is tailored, the theory that we followed and that we generalized is a wavefront following theory, which means you only try to capture what's happening with the wavefront. But surprisingly, and that sometimes happens, and when Juan Carlos showed me for the first time some of these figures, I said, wow, look what's happening. And Juan Carlos was very proud that the wavefront here, we have a theoretical curve and a numerical curve for this. Okay, for the Gaussian convolved with initial condition and so on. And it was working, of course, very well. But I was surprised that not only the wavefront was good, but this coda, which is o rabo, a cauda, as we say in Portuguese, the coda of the wave, which is this tail that kind of follows the wave, was also a very good approximation. Okay, and the theoretical approximation was stopping here. So you see this straight line here. And I told Juan Carlos, well, increase the window in which you're doing some Fourier integration, blah, blah. And it was amazing. Look here. Here you see the wavefront very good. You see the apparent diffusion. It's not that strong, but there is. Can you see the apparent diffusion? Look at this. Here's the wave height. It is smaller, and it's actually broader, right? So look at this. This separation here is smaller than this separation here. Yeah, it's broader. Plus, I mean, we compare the theoretical formula, and it's right on top. So it couldn't be better. And what was remarkable and surprised us, and I was very happy, is that actually the formula, which is this convolution, which is a little more complicated than just this Gaussian times this, it's a little more complicated. This convolution not only gave us a very good result, the theoretical convolution not only gave us a very good result for the wavefront, for which that was the target of the theory, right? And Berlian and Burge never did this numerically, so they were not aware that actually in their formula it was already working well too, is that not only it gave the wavefront, but it also gave a very good approximation of what was happening behind the wave, right? So we were super happy with this. And look, here there's theory and numerics, one right on top of the other. So this is a very good thing. So it's a scenario where the theory is an asymptotic theory, where there's basically a proof of a little lemma following Berlian and Burge. They also do. And it's a proof for a very special type of disordered medium. So we made more general. The rest is formal. I mean, there's no theorem. But then you do the careful numerics, and this illustrates the theory better than we thought, right? Because it was not for the wavefront, but afterwards. So this was very nice. And then we said, hey, the theory is working better than it was asked for, because the theory, as I said, is a linear theory. And it's getting, so we said, let's play a little bit with a small solitary wave, which means with a weakly nonlinear case and a weak dispersion, and let's see what the theory will give us. Oh, this is for for a case with just dispersion. So this is the flat bottom, blah, blah, blah. The other one, the case I was showing you before was with no dispersion, was like the acoustic wave. Here's with dispersion, and look, the theory. So you see the flat bottom, we have dispersion. And here you see the theory and the numerics, boom, one on top of the other. Okay? And a little bit also going in the direction of the answer that Márcio gave, which is hard if you don't have the intuition. Look how this rapidly varying part here, the tail of the dispersive part in the flat bottom, when it's in the presence of the disorder, you don't see any tail here because it gets immediately converted back as a reflected part. Right? So it gets sort of destroyed. Anyway, and I think the last figure I want to show today is, this is another dispersive one with more dispersion. Look at the height, the very long tail for the area function, and the theory. Look in the bottom, the theory and the numerics, right on top of the other one. Okay, and this one, I think, let me finish here. I'll come back to this one next class, but let me just finish here. I think this is the solitary wave. Yes. Okay, this is the solitary wave. And I'll come back to this last class. This is a good point for me to finish the class today. So this now here on the top is a solitary wave. This is the flat bottom test, right? Or this is the initial condition, the solitary wave, which you already tested, that we can make it travel as a traveling wave. And as you asked, Lucas, with no numerical diffusion, with no numerical dispersion to leading order, right? There's always a little bit. But the things that you want to tailor things, you want to calibrate things so that during your time interval, which your wave will propagate a long distance, this small dispersion that might appear, this small numerical diffusion that might appear, are not order one. They're not seen, right? I mean, rigorously speaking, there's error in the numerical method, right? But it doesn't appear in the time interval of interest for our study. So here it is. And then look, the solitary wave, the bottom graph is the solitary wave under the under the apparent diffusion. Look, it's smaller, it's wider, and the Fourier integral that Juan Carlos got, which is convolution type, more complicated a little bit than this one, gets exactly the solution very well, to our surprise. Okay? Next class, I will stop here. Next class, I'll show you a little more of this paper, a little more. I'll come back to this figure because it's next Monday, and I'll show you the numerical method to get all this, which is then a most important thing for this course, the numerical method. But what I wanted to show to you is to tell you a story, a full story of a research problem, typical of at least the applied math that I do, which is there's the PDE math modeling, there's the numerical modeling, and then there's simulations to either verify a theory, illustrate a theory, and sometimes also to start a theory. You do the numerical simulations to say, now I have some intuition, and that's actually how I convince some of my probabilistic experts to join me in another project, by actually doing the simulations first after I learned things from Juan Carlos' thesis. Then I did simulations first, and I showed to Jocelyn Garnier and to Jean-Pierre. I said, look, I think you guys can, make the probability theory to work because this and this and that and blah, blah, blah. Okay? But anyway, so we'll come back on Monday to this problem.